Okay, now let me start. Today we will reconsider an example as last time in order to consolidate this kind of controller. This means state space integral control, but integral in the context of the state space. Because this is basically an example which can be useful for the examination in this sense. Next week, we have 2 blocks, and I will consider a nonlinear control system. It could be that the first part I will dedicate to, I don't know, it could be also today I have time to show you something related to the eigenvalues. As I told you, I will update my study because I have to upload the lecture of last time, before last time. Anyway, I will update. Okay. Let me switch on the lateral camera and let me consider this example, which we have already seen, but in the context of the dynamics of the system. And now we will consider the dynamics of the control of the system, in which sense, in the sense that we will consider also the dynamics of the controller. Let me consider this. Just to understand what I intend. You remember? This system here. Let me orient the movement of the car. Positive. I hope you can see it. And it's not so. You can see in this direction. This is the movement X, let me say. X. Positive in this direction. We orient the movement in this direction positive. Then, if I consider the center of mass, I will consider again propulsion force, motoric force, positive in the same direction. You can put also a different direction, but in order to be more clear in the explanation, in order to avoid confusion, typically we orient positively with the same direction, would like to say force and movement. This means also the positive velocity is, let me say, toward right, or left, depending what to intend for left and right. But in any case, in this direction. As I told you, the model which I will consider is a model with concentrated parameter. This means we have a mass, as I called here, mass M, which you can consider concentrated here. This is very important concept in the model. We are not here exactly to analyze the modeling with its identification methods, but in any ways, as I told you, that concentrated parameter means that the mass of the whole car is concentrated here. Of course, is a strong simplification, because the mass is distributed, and not only if it's concentrated, I neglect the form. But this is not exactly something which we can say that the model is precise, because the aerodynamic structure of the car plays a crucial role in the friction, the air friction. This means for the lecture is okay, for a project we have to consider a different model, which we can consider also, the shape and the sex. M is, let me write so, the concentrated mass. Let me take a little bit more place. I clarified the word concentrated. in the center of mass. Yeah, center of mass probably is known from technique mechanic or for I don't know in which course. Basically, is an equivalent point in which we can consider, this is a little bit, is explained really colloquially, in which we can consider an equivalent point, an effective point, which we can consider under some assumption, in which we can see an equilibrium point, if you want, but of course a little bit more concentrated, more complex, the concept of center of mass. Probably you remember, it's an integral anyway. It's a concept of which I don't have time. It's not the goal of our dynamical systems here. But anyway, you know probably what I intend. Then we can consider B. I think we call B the friction. Mass is kilogram. I don't need. Let me write kilogram. B represents the friction coefficient. Sometimes damping coefficient, but damping is more related to the dynamics. Friction is more related to the physics. Friction coefficient, which imply friction coefficient is Newton multiplied second divided meter, which imply Fr, the friction force, equals, let me say at this moment, B multiply X derivative, the velocity. We will see a little bit better inside Newton law, but I already told you once about this model. Probably you know from different course too. Yeah. X of the position. What is already clear here, but let me rewrite again. X derivative equals velocity. Yeah, very often we write X dot of t equal XV, no? And sometimes X equal XP exposition. But let me write, so let me go ahead a little bit faster. You remember the moment we have seen, but probably you remember for other courses. It's extremely easy. Moreover, I have to add the initial condition. Let me say, for instance, something like that. You know probably directly from math. Newton balance. Inertial force equals motoric force minus the friction. I don't need to comment this. Yeah, this means in accordance with I wrote here, we can write something like that. The derivative of the position equals xv, the velocity, and the derivative of the velocity equals what? 1 divided m, which multiply f of t, which is an input, minus fr, which is b multiply xv. Do you remember I told you a lot in the context of the friction force, how we can model this FR? And of course, I have to also include this initial condition. You remember, this is the form which we need, which we want, but we need also, because our idea is to represent the variation of the two energies which we have on this, which play a role in this phenomenon in accordance with this data. Is the work, energy, the movement, and the kinetic energy. From here, you remember, we can realize now our vectorial, let me say, representation, in which we have x capitalized derivative, which is basically the vector of the the derivative of the states, the transition matrix A, which multiply again, multiply the vector now without variation, the state vector, which is X capitalized, plus, in this case, in a column vector, which multiply f of t. This column vector is the matrix P. Assuming that I want to control the velocity, why not, for instance? But try to do at home to control the position, but it's not a problem, because if I want to control the velocity, I have the matrix C that we will see together, which will multiply again as here. The structure is the same. We have to put on the right part the state vector as here and the input. Let me now fill up this matrix A, B, and C, and D. You remember this was the notation which we used until now. What about here? I have to represent with this new language the information which I have here. Of course, I have to add also the initial conditions, but anyway, this is not the problem. It's the initial condition. It's just in the vector calculate of the state, calculated times 0, which is 0, 0. It's in a column vector with 0, 0. If you want, I can. To be precise, this is not really a big problem to show you what I intend. In MATLAB Simulink, we have a similar time how possible to put these zeros. Anyway, this information here, not just to understand what I intend. What about this matrix here? Row multiply column, I have to get this information here. This means 0, 1. Row multiply column, I will get this information here. To get this information here, for instance, from the state point of view, I have 0 and minus b divided m. Why that? Because from the state point of view, I have to represent just on the right part, minus b divided m multiply xv. This means row multiply column, I have to put here minus b divided m. But of course, here, I have also 1 divided m, 1 divided m, because I have to represent also the force in input. Here I don't have input, this means I will put 0. No? What about the output? If I want to control the velocity, typical cruise control, I have to put 0, 1. If I have to control, if I need to control the position, parking problem, I have to put 1, 0. No changes. Here, in any case, is 0. Because the idea is to obtain xv. This means mathematically, trivially, we have row multiply column, xv equal xv, I would like to say this is valid, plus 0f. Sometimes you remember this d is not 0, depends what I want to control. Try to do at home to control acceleration. If you control the acceleration, you need here something. Try to do it. We did together. Okay, let me now a little bit speed up. Not much. 1 second. I repeat it for you. Yes, this is in the slide from let me say from another lecture. Forget this page number 14. But if you want, I write here 13. So you find in my study something which start from 13 and go ahead. Because this lecture was included in another program. This is the why this strange sentence. Let's consider the system of question Q3. Doesn't matter. Forget it. This is the let me say. 1 second. I have to close. I repeat, I copied for you the information of the dynamics. Now, as last time, we redo the exercise not in order to consolidate our knowledge. This This we will find this in the lecture. Excuse me, in the lecture, of course, in the exam. Basically, in the exam, I will propose this kind of control. The goal is to analyze the dynamics, and we are here for dynamical system, of the controlled system. Basically, system, let me say, plus controller. But plus, a little bit strange, but a system which includes system, yeah, a little bit, let me see, our control system or controlled system include the system and the system and the controller. We want to analyze the dynamics of these two structures when they are combined together. We call it controlled system. Okay. Also, this I will put in the text of the exam, because the controller must be given. What is the meaning of must be given? Practically, when we are working in projects, we try to conceive a controller. We try to think about the characteristics of the controller based on our experience, based on our intuition. Now, okay, we are not in the project, we are in the examination. This means these two information I will give you. Here is the characterization of Xi. Now we have seen last time. Xi represents the pseudo state or the augmented state of the integral of the integral part of the control. This kind of controller, again, to repeat, consists of two parts. We can see here a state space controller and an integral controller, which we will represent also in a state frame. This is extremely interesting, this controller, because of the presence of the integral. You remember the integral characterizes always the memory. You remember I told you many times, or if you want, you can recall this knowledge from the high school. The integral represents summation. The integral represents accumulation of data, of course, of information. Is the memory. Store or the storage is something related to the energy. This is the new or the augmented state which characterizes the integral. We can see directly from them. So we have basically now three states: X, XV, and XI. X, XV, and XI. Both, all three, excuse me, both plus this are characterized by integrals. X is the integral of XV. XV is the integral of the second equation. XV is the integral, let me say, of the second equation. Xi is the integral of the error. The error between what? R of t is the reference signal. X of v is the state, the velocity. If I want to control the position of auto parking structure, we have X here. Very easy. But Xi does not change, in the sense it's the integral of the error between the desired position which I want to obtain minus the position. Here is the desired velocity minus the velocity. It's up to you what we want to control. No? It depends on the project. In the exam, of course, I can also consider to control the acceleration. You can do. If you want, I can prepare I have an example which I control the acceleration. It's also an impossible problem. But more typical, cruise control, velocity control, or auto parking system position control. Okay, here I already explained everything. Now, plug it in, as last time, this expression here. This expression, u, f of t, u is another notation, f of t, is the same f of t here. Why that? Because you remember I told you f of t here is the same f of t here, which we call very often u. The output, what is the meaning? The output of the controller is the input of the system. It's not a definition. or at least in this context, it's so, isn't the definition. The controller is a function of states. Of course, this controller, even though in a function of states, consider the difference also between the goal and the state which we want to bring, let me say, to take to the goal, the velocity. 10 kilometer per hour, let me say, the goal. And here, minus the actual value of the velocity, which is the state of the system. Plug it in this expression here. I will obtain this. Just instead of f, look, I put here, is instead of f, I put here. Believe me, is f of t is this, let me say, complex expression, if you want, in which xi is again this, no changes. Recall, xi is the state, the state of the controller. In some books, they say augmented state, pseudo state. Why pseudo? Augmented because we augment the original dimension of the system with another state. Pseudo sometimes because it's the state of the controller is not exactly the state of the physical system in the sense, but it doesn't matter the name. Yeah. Now I can mathematically write these three equations again, if you want. Basically, from here, if you do rho, let me say, if you do rho multiply column, and then we have to consider this vector here, we can rewrite everything in the equation form, if you want, in this form here, in which we have x dot is equal to xv, no change. Xv now, instead of f, do you remember, was 1 divided m multiply f minus b divided m multiply xv. This remains, but here instead of f was f divided m. I have to write what f is. And you remember, rho multiply column minus k11 multiply x, the position, minus k12 multiply xv. This means this rho multiply column plus ki, this rho multiply column in scalar function. This rho multiply column is scalar function. Minus this, minus ki multiply xi. This is exactly what I wrote here, everything divided by m. Now, as before, I can write this expression here is in the form of matrices and vectors, because this is the controlled system in terms of it. This is the controlled system in terms of equations. This is the same controlled system in terms of matrix and vector. We have this vector here, the derivative of the state variables. Then we have a matrix A, which we multiply again the state variable without derivative. Now, this is the same example, structure, the same example, if you want, which we have seen many times at this step here, plus the vector 0, 0, 1, multiply r of t. What is the difference here? The difference is, but we don't need to analyze the difference. Rho multiply column, I have to get this information, therefore 0, 1, 0. Here we have just xv, no component in f. This means 0, in r, excuse me. R is the new input, if you want, the reference input. Rho multiply column will get this information here. It's a little bit more complex than before because we have these three elements which must be represented or reflected in the equation. This multiplied this, k11 multiply x divided m is here with minus. Then we have, what is the component of xv? We have minus b divided m xv, and minus x12 multiply xv divided m. This means this element here, which will be multiplied by xv, represent or translate this element translates the component or the contribution of xv in this form. I don't know if it's visible. Minus b divided m is here, we will multiply by xv, and minus x1, 2 divided m is here, which will multiply by xv. The same concept for xi. I mean, this component here, this element here, divided m, of course, must be also present in this expression here. This means when I do row multiply column, this element here multiply this minus chi divided m multiply xi represented this element divided m. This means it's full this let me say this expression here. No r, in fact, 0. Why here 0 minus 1, 0 as last time, row multiply column, I need to get this minus xv, thanks this minus 1 I will be able to do. And of course, r is present, means I have to put 1. Again, r, the reference, 1 meter per second, 10 meter per second, I don't know what, is our new input, which is a new reference. It's the reference, which is the input. No? And I will clarify a little bit the concept of the input in 1 minute. Yeah. If you want, I can anticipate this concept of the input. I think we already seen this. Yeah, we already seen with MATLAB at least once. Look at the scheme, and then we will come back on the scheme later. The system. I measure x and xv, position and velocity. I need the information about the position and the velocity. We can see here, I will multiply k11 by the position. I will multiply k12 by the position. I sum, you remember, because it's the sum of the two contributions. Let me show you this concept here. Row multiply column. No? We have the sum of these two contributions. F of t as the sum of this contribution, of course, or the linear combination, better to say, of these two contributions, k11 minus k11 multiply x minus k12 multiply xv. And then we have this one, but this part here is the linear combination, which can be represented in this form here, with minus for both. No? If you remember this block diagram language, or block diagram language, something like. But I have also to consider here, as f of t, the integral of the error between r of t minus what I want to control, xv, if I want to control xv, if I want to control x, I have to have the information about x, this position here, with a minus. F consists of 3 components, 2 from here, and 1 from here. It's exactly what I have seen here. Yeah? Of course, this minus here is represented here. Eh? Clear. Plus minus represent what we have inside the integral. Eh? Okay, here I already told you where we were. Because I lost now everything. Yeah. Now it's a little bit more complicated, but I try to explain again. Until now was relatively easy. Now, if you look at this structure here, we have here a system which is represented in state domain, which we have x derivative as a vector and a matrix. This now we will call in some books extended. Multiply x plus a vector b. Multiply the input. It's exactly what I told you many times. What we have seen also in MATLAB. We have this structure of the linear system. We are looking for a matrix K, which we will call K augmented in this sense. We will be calculated. You remember last time I told you a lot, we have seen also in MATLAB, the function place. Why I'm insisting on the function place? Because at the end, we have to solve a linear system in which I would like to calculate this parameter, which are the parameters of our controller, which guarantee hemodynamics, which is reflected by the eigenvalues, which I can fix as I want in accordance with my specification. I can, do you remember, fix the speed of the system. I can decide if the answer, the speed of the system means the speed of the answer. I mean, if I have to reach 1 meter per second as a velocity, I can decide to reach 1 meter per second in 1 second. I can decide to reach 1 meter per second in 10 seconds. Of course, this state, let me say, the velocity, let me say, of the control system. And this is reflected by the position of the eigenvalues. Do you remember last time? This means I have to calculate K11, K12, Ki, we will see now in detail, such that I will obtain some given eigenvalue in accordance with my specification. We will see together. We will not do by hand, we will do with the function place. What about the examination? In the examination, we have to stop at one point, you remember last time, which we have to include the computer, but we don't do the computer. I show you what I intend. Basically, using the function place, which should not be used in the exam, I put in a particular augmented function matrix with this dependent of a extended. We will consider a B augmented, we will say. And here in the vector, P is in a vector, this is a matrix, this is a vector, this is a vector. We will consider the desired or the requested, better to say, eigenvalue which reflect what we want to attain practically. We don't want, for instance, to have oscillations. This means the eigenvalue should not include imaginary part. About that, I will tell you in a few minutes. Now, look. What about A augmented, we can see also here, and B augmented and K augmented? If you remember what I told you in the context of the state space controller, this matrix here, which is the transition matrix of the controlled system, can be seen, because this is parameterized, can be seen in a linear, in a combination, we say, of an augmented matrix, which must be defined, minus B augmented, multiply K augmented. Now, here, in this expression here, we know what A extended is. We know what K augmented is here. But of course, we don't know A augmented, B augmented. But it's not so, let me say, difficult to see this here, because we have many, let me say, different way to proceed. But this is one of not possible, in which A augmented, and then I will clarify why, is A extended, in which I will put K11 and K12, Ki equals 0. Why that? Because this element here, this 3 element here, will, in accordance with this expression here, will be, let me say, will be the contribution, let me say, of K11, K12, Ki will come from this. This means A augmented is A extended calculated at this point. Then using now this product here, we can apply the identity, but this is easy because now we know what is A augmented. And we know what is K augmented. It is easy to calculate or to define B augmented. Let me show you what I intend. Here is basically the explanation again. The explanation again come from because the K elements come from the product B augmented, K augmented. Now the question is, what is this? If I put K11, K12, Ki 0 here in A extended in order to calculate A augmented, I will obtain this expression. is K110, I have a 0 here. Here in the numerator, I had minus B minus K12 divided 0, divided M. If I have a K12 equals 0, remain B divided M. Here, I had minus Ke divided M. This means I have a 0. Why B augmented? Why B augmented this one? Yeah, you can verify alone how B augmented is because this here minus B augmented, we have to calculate, multiply this row column with the K elements, let me say quickly. So I have to reobtain a extended. If you want, you can do also analytically. How B augmented looks like. But there is a rule, here is in the big explanation, the calculation if you want, which we can show that B augmented is exactly so. But there is a rule which say the first two components of the B augmented are exactly the same of the let me say of the physical system, because the input in this case just one, the map of the input does not change even though I have another equation, and the third one you have a 0 because the controller affects just the second equation in a sense. I mean, the structure of the system does not change in terms of inputs and output. This means here is the mathematical explanation why they augmented the structure here. But if you want to have an intuition, the first two columns, these two rows does not change because does not change the structure of the input structure of the system. And in this position here, in accordance of this controller, of course, in accordance of this controller, we don't have U. We don't have U, F in our case. U is F. Yeah, here exactly the calculation to explain why exactly this is this B augmented this structure here. Mathematically, if you want, you can put here a variable, here another variable, here another variable. I don't know. A, B, C. B is which element? A1, A2, A3, and then we can calculate that A1 is 0, A2 is 1 divided B, A3 is equal to 0. But intuitively, we can see exactly that if I consider this B augmenting with this idea, I will obtain after the calculation again A extended. Just to repeat what I intend. Yeah. Now, assuming that I don't want oscillations, and I fix the dynamics for the system, which reflects three new eigenvalues: lambda 1, lambda 2, and lambda 3. You remember last time I told you, now we will see together again. More concretely, what is the meaning of this lambda 1, lambda 2, lambda 3? I mean, how the eigenvalues of the matrix A extended reflect the dynamics of the controlled system. Let me proceed now mathematically. I will tell you about this. I think we will start today with a presentation in order to recall where this equation comes from. But from math, probably you remember. Now, just mathematically, we have the matrix A, which in our case is an extended matrix, and the eigenvalue of the matrix A can be calculated with this equation here. We will see together where this comes from. But now our problem is not exactly this, because the eigenvalue of the matrix A, in our case A extended, depends, excuse me, from the matrix, the row matrix K, which consists of minus K11, minus K12, minus Ki. This means the problem is the contrary. For given lambda, this means for a specified dynamics, calculate K11, K12, Ki with this equation. Look. this expression here is rewritten here. Doing this calculation, probably I don't have to explain how we can do this calculation. This matrix minus this matrix. I have to consider this element minus this element, minus, and so on. The determinant of this must be 0. If I have the value of lambda 1, lambda 2, and lambda 3, of course, with the computer, the computer does this in a few seconds. We have seen last time, a few seconds, nanoseconds, in which if I assign lambda 1, lambda 2, and lambda 3, the computer will, using MATLAB, for instance, with this place function, we will calculate very quickly. We don't do that in the exam. For instance, in the exam, I will tell you, please consider the new dynamics. The new dynamics is the control dynamics, at least 2 times faster than the physical system. Now, here, why I consider minus 2 b divided m, minus 3 minus 3b divided m, minus 4b divided m. If I am saying you at least 3 times, this means that the minimal eigenvalue in absolute value must be at least 2 times the eigenvalue or the minimal eigenvalue, absolute value of the minimal eigenvalue of the original system. Now, I don't know if you remember, we calculated the eigenvalues of a car, let me say so, which is characterized, or better to say the real part, to be precise, at least 2 times of the smallest real absolute value of the real part of the original system, of the physical system. So complex I will not give you in the exam. I will put lambda 1, lambda 2, lambda 3. Because otherwise you have to calculate the eigenvalue of the original system. I don't know. It should be possible, nevertheless. Should be possible. If you want, I don't know if I have here. I will tell you, because also this is important, the dynamical system. Why I'm considering this, and then 3 times, 4 times, because you remember last time I told you the dominant dynamics is this one, which is the minimal real part of the eigenvalue in absolute. When I take this in absolute form, let me say. And we come back on this a little bit better in a few seconds. Even though I tried this to explain in this text here. The original system has lambda minus b divided m here as a real part, no? As a real part. I didn't wrote, but it's implicit. It is implicit. You remember the concept of the dominant time constant, which is the largest one, which corresponds to the minimal absolute value of the real part. This I already commented. Let me try to be really clear what we can do in the exam, because it's a little bit unclear probably, but let me show you a clear. I will give you the following specification. Yeah. Call, please. Speed up the system, the original system, so we can understand. The original dynamics better. This means the dynamics of the car. Such that the controlled dynamics results to be at least 2 times faster than the original dynamics. Now, this means I have to calculate how the original dynamics, how fast is the original dynamics. And this solution is first of all, I have to calculate how fast is the original how we can calculate? I have to calculate the lambda. Now, the lambda reflects, the eigenvalues reflect the dynamics. I told you last time, I repeat it. Now I will repeat again. This means, what is the original dynamics? Let me write this down. Remember. So, no? This was the original system. I don't have much place to let me write quickly. 0, 1. Remember this. We have seen, I discussed with you this. We have seen many times. I don't need to repeat. This is the Amazix. Now we will see, I think, the next week, why I need where this comes from. No? But you know already from math. Next week we will start with a formal lecture on this topic here, and then we will change the nonlinear control. Identity matrix with the dimension of A, 2 times 2. This means Determinant of what? Lambda minus 1, 0, lambda plus b divided m. This imply lambda 1 equals 0 and lambda 2 equals minus b divided m. Now, in accordance with what I told you before, this is the definition of the, let me say, time constant with respect to the lambda. Of course, lambda should be not 0. This means we have just one lambda, which is this one. This means 2 times at least faster. We can justify exactly this. 2 times, 3 times, for instance, but you can put here 30 times, 40 times. Okay, it's not exactly the same, but you remember, very important to think that this lambda defined the dominant dynamics. Because you remember, I told you last time that the dominant dynamics is characterized by the largest tau, which is characterized by the smallest real part of lambda. Why I have just, I put just a real part? Because I don't want oscillations. This, we will come back on this point here, but we have seen when we have a lambda complex, we have oscillations. Well, yeah. This means in the exam, at the end, we have to consider this expression here, and let me see how I can formulate finally I think we can see in this form the final expression which I have to see in the exam. Let me take something to write. If I find, this is another issue now. Second. Probably here once. I try to find something great. I have here, but I don't find it. Okay, let me 1 second again. Okay, let me cancel here and then I come back in 1 second. Otherwise, I can try to. Yeah, let me try. Determinant of this, in which lambda 1, lambda 2, lambda 3 is given. What is the determinant of this? Remember that you this which multiply this minus this multiply this. Which multiply lambda minus this multiply this. then we have minus plus, let me say, minus 1 uh, up to 3, which multiply this element here. Yeah, basically, I don't know if you remember, we have minus 1 up to 2, therefore I will input. I cancel this row. Yeah, minus 2. This minus 1 has the definition up to j, I, the row 1, and the second column. This means up to 3. You multiply this element, and then I have to consider the minor cancel without this row column and without this row. This means this multiply this minus this multiply this. Okay, I think no mistakes. I think no mistake. I think no mistake. Again, this is this multiply this minus this multiply this is okay. Here I have to consider this element here. Minus 1 up to 1 row plus second column up to 3, minus 1 this element. I cancel this column and this row. I will obtain this minor characterized by this, and this. This means this multiply this minus this multiply this. I think everything's perfect. This means we have a system of 3 equations and 3 unknown, which is lambda 1, which we define also lambda 1. Remember, minus b divided n. B is given as n. Yeah. This is plus 1. And then everything the same, but with lambda 2 is given. Lambda 2 is calculated. I explain also how I calculate it. And then lambda 3. Let me see if I see mistakes. Again, here, what is unknown is K11, K12, and Ki. I forgot Ki. I forgot Ki. Ki should appear. Let me see. One second. I'm too fast. Yeah, again. This which multiply. This okay, here. I forgot Ki. Yeah. This is Ki. Excuse me for the error. Yeah. Because it's this multiply this. No? Okay. The unique unknown. to be calculated, of course. Of course, we don't do in the exam. No? We stopped here because this is in the three equations, algebraic equation, and three unknown. If the system is controllable, we have always a solution. But about the controllability, I didn't tell you much. Yeah. Let me reorganize here with the material. Next week, we will start reconsidering this concept of the dynamics, time constants, real part, imaginary part of the lambda. This we will go really in depth in the first part. The idea is also, let me enumerate a little bit. I think this is 20. The idea is to go in depth on this. Where this comes from again, from math, and then how lambda characterizes the dynamics of the system, the original system, but also the control system. In one case, I have to calculate lambda. In another case, for decided lambda, I calculate the parameters of the controller which realize our specification. In terms of no oscillations, this means no imaginary part of lambda. And if I approximate the dominant dynamics with the largest real part, let me say, of the large time constant, which is 1 divided absolute value of the smallest, excuse me, 1 divided this smallest absolute value of the real part of lambda. I think I expressed correctly. We can now obtain the specification in terms of lambda. Of course, it's an approximation. But of course, using the simulation, we can eventually adjust. It's an approximation in which sense? Because basically we have three dynamics related to the three eigenvalues. And yeah, we have an expression of the solution of the possible output in the sense. Output is the velocity, no? The profile of the velocity. This means, how possible to say, theoretically, we have to define a little bit more clear what was the time constant. We have a three time constant. In any case, we can consider the dominant time constant as the rising time. I don't know if you remember, I told you a little bit the last time about the rising time. It's the time in which the velocity will achieve, let me say, almost 70% of the final value, of the desired final value. But anyway, these aspects here are more related to in a project than to the examination. This means I will formulate probably in the sense what I told you before, at least 2 times faster than the physical system which we are considering. And then you can consider in this case, for instance, minus 2 times b divided m, and then 3 times, minus 3 times b divided m, and so on. If I write, please, at least 2 times slower, and I have to divide it by 2, and think about. This is nevertheless is easy, divided by 2, divided by 3, divided by 4. The dominant time constant. Of course, if you have a 2 time constant of the original system, what is the dominant? The largest one, in accordance with the possible definition. Of course, it's an approximation because the answer is in a combination of 2 exponential functions. You remember, as I told you, but Remember last time I showed you what is the dominant, what is the meaning of the dominant. It's extinguished slowly. Okay, next week, nevertheless, as I told you, we will go in depth on this determinant of lambda e minus I equals 0. I will reconsider also dominant eigenvalue. Yeah, why not? Well, dominant eigenvalues, better to say dominant dynamics, which reflects the dominant eigenvalue, that reflect the dominant time cost and so on. And then we will start with nonlinear analysis. Nonlinear analysis. Yeah, next week is February the 3. I will tell you when I will do. I don't know when we have the exam. No? This means we have to, because from the calendar we have just one lecture, right? Because the 10, I don't think so. We have a lecture, but I will check. And the problem is we have to really look when we have the exam. My idea was to, anyway, I will check when we have the exam, and then not later than next week we will discuss for the tutorial or tutorial. But anyway, per Zoom we can do also in the evening. So I don't remember when the exam. I will check. Today I will upload all material. It's the time to have all material in my study, so you can start to recap everything and so on. We will see next week. Let me say more or less 8:30. Thank you really for your attention. We will see next week.